Hey, it's Mr. Allred, and I want to cover a few things we did in class. This is Calculus 3 material, and I believe it's from section 14.3 in the book. But we're talking about multivariable functions, and we'll get into partial derivatives as the main reason we're here. So, just as a kind of a quick overview, a multivariable function usually has multiple inputs, as we see here. So this function is named f, and it has input values of x and y, or input positions of x and y. So two things are going in and one thing is coming out. So you can kind of think about that as an x, y, z function. But we could have even more than two variables going in. So we could have an x, y, z going in and f of x, y, z coming out. So we could be talking about four variables, which might be a completely different idea of graphing. But if we're talking about an x, y, z, or two inputs, one output, you can see kind of the three-dimensional topographical graph we have over on the right. So just to kind of point something out here, I plugged in the point 0, 0, and I got back 1. So I guess that's somewhere in the middle here. I don't have this where I could turn it, but 0, 0, 1, if I tried to plug it in, it has an x, y, I'm calculating a z. This here, I plugged in 1, 0 for x, y, and I got back 1/2. So I don't know that I have this in the best way, but somewhere along 1 and 0 and 1/2 might be around here. But it's a little bit hard to visualize these unless you have something where you can move it around. So let's see here. Let's go to my next slide. So partial derivatives are how we're going to talk about the slope. So we've got here partial derivatives of a function measure the slope in a certain direction. So over here on the visual, let's see here. Let's use something like blue. I could come to the central point here, 0, 0, 0. Maybe I need something bolder than that. So let's try that again. Something bolder than the blue. So 0, 0, 0. Well, 0, 0 is the input, and the 0 for z coming out is the output. But if we measure this thing as a rate of change in the x direction, and look where my axes are labeled here. If I go in the x direction, I'm going to come up a curve. So that's a positive slope here. If I move along the x direction from that point, and for the y, if I move in the y direction, it's a negative slope. So when we talk about slope, we kind of have to talk about it in a direction. So if we move in the x direction, I didn't mean to make it look like that, but if we move in the x direction and the y direction, it may look a little bit different as far as whether or not it's growing or decreasing, so following along there. So from any given point, we might have different rates of change if we go in different directions, since it's three-dimensional. So partial derivatives here, you can take a partial derivative function for one variable at a time. So as I was drawing on that graph, we could see how something is moving in the x direction or the y direction, okay, but not both at the same time, not yet anyway. So I said if you take the partial with respect to x, that means you're trying to figure out how the function is changing in the x direction. You'll take a derivative, but you'll treat y as a constant. And so this gives you the slope in the x direction. So in our case, f over x, delta f over delta x. We can do the same thing with respect to y. So let's kind of see that in action, and let's see the notation. So I have the function f of xy equals x squared minus xy plus y squared. So there's really two different partial notations. One of them's kind of hard to write. Mine kind of looks like a 2 when I do it, but that's the partial of f with respect to x is what we've got here. That's how it looks like in the traditional rate of change definition or notation. Sometimes you'll see it as the function name f with a subscript of whatever variable you're taking it to. So f sub x, which makes a little bit easier to write. But in this case, we're treating x like a variable. So when we come up here, derivative of x squared would be 2x. Derivative of negative xy, we're treating x as a variable and y as a constant. So if this was negative 2x, we just get negative 2. So treating the y just like a number, we get negative y. And then the last one, y squared, doesn't have an x, so it's just like plus 5. So when you take the derivative, you'd have 0. So the partial with respect to x would be 2x minus y. So you're treating y as a constant, but if it's a multiplier, it still may be left in the expression. So here, partial of the function with respect to y, and I didn't write the notation down here, so let me pop that in here. So that would be f sub y. But x squared doesn't have a y, so it goes to 0. Negative xy will just leave me with negative x, once again treating the x as a constant. And y squared, the 2 would come out front using the power rule, so 2y. So we can clean that up. Okay. At this point, notice that the partial with respect to x tells us the slope in the x direction. The partial with respect to y tells us the slope in the y direction. But even in these formulas here, if I write it out, f sub x equals 2x minus y, I need both an x and a y to be able to calculate that slope, because just plugging in an x kind of doesn't narrow it down in the three-dimensional field. So we're looking at the xy plane as our input, so if I just say x is 3, there's a whole line where x is 3 and y could be anything. So if we want to narrow it down to a specific point and actually talk about how it's changing at that point, it's not rare that we would still need both the x and the y variable to narrow down that location. Let's see what we got here. I just got some more examples. So this function is x over x squared plus y squared. So this is the partial of f with respect to x, and I didn't write it over there, so over here f sub x. It's a quotient rule. So u over v, and you will see v u prime u v prime over v squared, and it's just carrying that out, treating y as a constant. So in that case, when I take the partial with respect to x, I get y squared minus x squared over x squared plus y squared all squared. And I can do the same thing at the bottom with the partial with respect to y. Some things cancel out, but I get the same idea. Okay, so let's see here. Let's do another one. So pause at any point if you need to take a look at what's going on. So then we get to the second partial derivative. Okay, second partial derivative notation. So first of all, we have to take a first derivative, then a second derivative. We just don't jump to a second derivative. We've never done that. But in this case, we would have the partial with respect to x, and we have the notation for that. It could be either notation. So what's neat about this is once we take the partial with respect to x, we can take a second derivative, but we could take it with respect to x again, or we could take it with respect to y. And we see the two notations down here, and it's important to note the order here. So here we have xx, f sub xx. That means over here, in this case, this first one, x, is the first derivative, and the other one is the second derivative. If we use the differential notation, it's actually backwards here. It reads from the inside to the outside. Okay. And same thing on the other one. Notice xy. So we said we were taking the derivative with respect to x and then with respect to y. Over here you'll see it once again the same order. X on the inside, y on the outside. So the first derivative that's done is the partial with respect to x, and then after that you take the partial with respect to y. Let's see what we got here. Here's an example. The function is 5xy minus 7x squared minus y squared plus 3x minus 6y plus 2. So pretty easy thing to work with, especially if we're always treating one of those as a constant. But kind of follow down here. we're taking the derivative with respect to x, the partial. So we get 5y minus 14x plus 3. Now we can use that to take it to the second partial with respect to x, where x is still just a variable, and we can also take it down to the other one where we take the second partial with respect to y. So even though I've got it written two different ways, it's two completely different things. So it comes out of the partial with respect to x, then you can take another partial with respect to x, or you could take a partial with respect to y depending on what you're being asked. Okay, but there's not a link between the second partial of x and the second partial of y. There's no link there. In the other side, we're starting off with the partial with respect to y. And we get 5x minus 2y minus 6. So from there, we could either take the second partial of y, or we could take the next partial with respect to x. Okay. One thing you might notice here that's kind of interesting is the mixed second partial, is the same. So f sub x y is the same as f sub yx. So that mixed partial gives you the same thing. Let's see here. So here it is written out. It's not as neat as I'd hope it would be. The differential partial notation is very hard for me to make it look neat or consistent. But notice that we did change the order down here. So that's the first operation, and then after that the second one. But they're equal as long as you do them correctly. So here's another example. W equals x sine y plus y sine x plus xy. Not the hardest thing in the world, but you could come down here again and see that the second mixed partials are the same. They don't have to be in the same order. But you could walk through all these steps and make sure that you see where all the partial derivatives are coming from. And I got one more example here, and got a little messy, but in this one we're actually going to use the second, well, not the second, but the partial. The function is f of xy, and it's x times the sine of 2x minus y squared. And it says we're going to find the partial with respect to y, the partial with respect to x, and we're going to plug in the value for x being pi over 2 and the value for y being just pi. So we just only need the first partials of each, so we don't even need a second partial or a mixed partial. But taking the partials, you can come through here. Partial of x, you treat y as a constant. We get down to sine of 2x minus y squared plus 2x cosine of 2x minus y squared. Plug those values in, pi over 2 and pi. I get that value to be 5.2414, and make sure your calculator is in radian mode if you're plugging them in as pi over 2 and pi. The other one here, the partial with respect to y, we're treating x as a constant. The partial with respect to y is a little bit neater, since you don't need a product rule because x is considered a constant there, but you get 2xy cosine 2x minus y squared. And pushing that through a calculator, plugging in the two values for x and y, I got 8.909. And that's what I got as far as pushing that through. So the function is at that point, pi over 2 for x and pi for y. If we move in the x direction, the output is growing at about a rate of 5. If we move in the y direction, the output is growing about at a rate of 9. So growing differently in different directions. So that's what the partial will help us do.